So today I will be talking about classification of viral, bacterial, and COVID-19 pneumonia using deep learning framework from chest X-ray imaging. This is Dr. Mahmud Chowdhury from Qatar University. I'm assistant professor in electrical engineering department. If you're more interested about me, you can check my web address. I will be talking briefly about the history of how we come to this, the work I'm going to present today. And I will also show some follow-on works our team is doing last couple of years. So I'll start with one of our paper, which is right now around 1,000 times cited. It's called Can AI Help in Screening Viral and COVID-19 Pneumonia? It is published in IEEE Access, and it is published in 2020, beginning of COVID pandemic. So at the time, there was a lot of scarcity in data. So what we did, we get some X-ray images which are publicly available from the Italian Society of Medical and Interventional Radiology dataset. And then we also get some dataset from Kaggle and other publicly available resources. So we make our own datasets, which is from 423 COVID-19 image. And also from Kaggle, there was a dataset publicly available from 2019 onward. So it has like 1,579 normal lung X-ray images. And also in that same dataset, we have 1,485 viral pneumonia images. So we make this dataset and we make this dataset publicly available in Kaggle. And we didn't intentionally publish it. We made it for the researcher so that researcher can use it. But then at the same time, there was a competition going on Kaggle, and we become like the winner of that competition because of sharing that data set, because people are looking for the data set at that time. So then we investigated our framework using that data set. If I can move it a little bit outside to be better. Okay, so you can see out of 423 COVID images, our model, actually deep learning model, managed to classify most of the, only 3 images are misclassified. And some normal images were categorized as viral, and some viral images also categorized as normal and COVID. But interestingly, COVID was significantly classified well. And at that time, only 2, 3, or maybe less than 5 articles on X-ray image-based classification are available online. Some are in preprint, some 1 or 2, I think, published. So very early work. So we tried a couple of deep learning networks, and CheXNet, some of you might have heard about that. This is a network released from Stanford Machine Learning Group. And this network is a derived version of DenseNet 1-to-1. It's a deep learning network, but originally DenseNet 1-to-1 was trained on very large ImageNet dataset. But then Stanford group then trained it on X-ray images, like more than 100K X-ray images. So it is like fine-tuned on X-ray images. So we found that even with this CheXNet, we are not getting the best performance, but for this particular data set, we got DenseNet, which is actually a deeper version of CheXNet. CheXNet is 1-to-1 layer, and this is 201 layer, so more deep network, and we got quite good performance. So that actually motivated us why COVID can be identified by the deep learning network. What is the signature in the lung X-ray image? So we look into it. So we found that actually, if you see here, this is the normal image, X-ray image, but not in the first layer, but in the deeper layer of the deep learning network. We found that in the normal X-ray image, there is nothing very visible on the left side. If you look at the left side, whereas on the right side, the COVID one, you can see there are some signature in the lungs of infection. And we found that in also in viral pneumonia, also this is COVID is a viral pneumonia as well, but other typical viral pneumonia like community-acquired pneumonias, we also saw some infections in the lung, but that's not same as COVID. COVID infection signature is completely different compared to other viral pneumonia. So that's motivated us, and also I think a lot of other researchers. After our publication, I think there are thousands of publications come up with X-rays. A lot of people used even our data set. You can see that. So this paper cited 1,000 times. So lot of works. So then we also check why some of the images, 3 images misclassified. So check in the deeper layers, we found there is no such signature. So then we check with the radiologist why deep learning network is failing these 3 images. Then they said actually these are very early stage COVID. So lung is not still infected. That's why deep learning model cannot identify that. So it makes sense. So then we thought, okay, since deep learning model is so good in identifying COVID-19, can it distinguish COVID from their other family members like SARS, MARS? Those 2 also have coronavirus infections, and they also infect lung. So, but the problem was it was happening in 2003 and 2010. You all know SARS and MARS, but the data set is not that available. So we search everywhere in the internet, all the repository papers, everywhere, wherever they mention this is MARS image, this is SARS image. So we collected from there and we create our own data set, and we investigated, and that's also published in Cognitive Computation in 2021. So you can see here, the data set has 423 COVID image and 100 plus and 200 plus SARS and MARS image. And these are the image resolution. So you can see it's not like great because of the internet collections. So some images have very high good quality, some are very poor resolution wise, and also patient lung condition wise. So we thought, okay, at the same time, there's a paper come out from Stanford group. They said, if you are using chest X-ray for training deep learning model, it might learn this L. You can see the capital L letter written here. So it might learn from this L, and this L can help it, or sometimes it learns from portable word. There is a portable word written on the X-ray, and they understand this is something severe patient, because portable X-ray is used typically for the severe patient. So then they said, okay, we should only give deep learning model, which is important area, which is called region of interest, ROI. So then we plan to get the lung segmentation. So you can see this is the plain X-ray, and we also did the lung segmentation. So since our data set is small, we can easily manage the lung segmentation. So I'll tell some story regarding that in the coming slide, regarding this lung segmentation. So, before applying just plain X-ray, we said, okay, should we try different contrast, because the image was varying a lot, especially MARS image was varying a lot in terms of contrast. So we said, okay, let's try to do some image enhancement. So this is the original image, and this is the corresponding histogram, bean of the every single value. So you can see the intensity, occurrence of the number of occurrence for every grayscale levels, 0 to 255. Now, if you make it histogram equalized, then you can see it is spread over the entire 255 bins. So now here you can see if we use CLAHI, which is a regional enhancement of the image looks much better. And actually later on, lots of paper come out on this CLAHI, because CLAHI looks like very potential for X image. And so we first time used on this paper, CLAHI. And then we also tried, because when our radiologists, like friends, they say, whenever we get any X-ray, there is a button in X-ray machine, like keyboard, they can invert the image immediately. So by inverting it, they can see more deeper picture of the image, like other things which are not visible in the original image. So then we said, okay, why don't we try that one for training the deep learning model? So we tried all these original, HE, and CLAHI, and also complement. And these are the framework we used. So you can see original image, we pre-processed it, enhanced it, and use deep learning model called UNet. It's like U-shape. So that's a segmentation model for segmenting the lung area. And then we superimpose both of these results to produce this only the lung area, because then it is focused to the region of interest. Then you use deep learning model for classification of COVID, MARS, and such. And this is some of the results of the UNet model. So you can see on if the image is good, the patient lung is not severely infected, then our model actually managed to get good lung mask. And this is the initial mask produced by the model, and this is after superimposing. And this is, we fine tune ourselves with the help of radiologist to make the more mask reliable. Then we found that actually for severe lung problem, the model significantly failed. Model cannot produce reliable mask. And then we need to modify it with the help of doctors so that we can get the correct area. So that's motivated us for another work of creating a very good model for lung segmentation, which I'll be showing in a bit. So these are the results for original image. So original X-ray, complement version, Clahi, and 3-channel. 3-channel means concatenating original with Clahi and the complement together. So we take the benefit of other image enhancement. So you can see for complement one model, a shallow model, which is QU-MLG, failed significantly, but the deep models perform more or less okay. But when you combined, then we found that actually one model here is like Inception V3, is performing significantly better when you combine the 3 techniques. So then we tried this same on the segmented data, but we found not the same behavior here. When you segment the data, because the region of interest now precise and model don't see other things other than the lung. So more or less all models performance are similar. Actually, we found that now original image is performing better than image enhanced version. So that's the like a summary you can see the confusion matrix. So this is the performance on the original image. This is the performance on the segmented image. So original image provides slightly better performance than the segmented image, which makes sense because in original image model can get some additional information to learn, but in segmented image is only learning from the lungs. But although this result is slightly poor, but this result is more reliable because now model is learning only from the lung area. So if you in a tabular form summary, you can see, so we can actually classify very well even COVID families, although they are from coronavirus, but their signature on the lung are not same, they're different. So that's what we concluded. So, and this is the segmentation, segmented version. So you can see results significantly dropped, but the reliability of the model increased, we can say. Now, if we look at how we say reliability of the model improved. So we look at the explainability of AI. So, you know, people are now talking how explainable your model is. So you can see here, original X-ray image, when model is learning from this area, learning from the heart area, learning from the like a middle of the chest area. But when you are giving the image, only it is learning from like segmented image and is only learning from the lung area. So even the result is slightly bad, but it is more reliable because it's learning from the correct area. Now, moving to the problem of today's topic, why we move into the viral, bacterial, and COVID-19. So I was showing the viral only classification, but if we show viral, bacterial, and COVID together, then the problem becomes challenging because a lot of literature shows that bacterial and viral infection signature on the lung are similar. Without proper clinical evidence, it becomes very difficult. So, and we published in 2019 at the end of 19 paper to distinguish viral pneumonia and bacterial pneumonia. So here we have this data set, a very large normal data set, 8,000 plus, and then 3,000 plus COVID image. We keep on gathering COVID image and same viral image and the new this bacterial class. So we categorize them into 4 class problem, and then we use this framework. We take the original image, and then we did some pre-processing, and then now we tried 21 different deep learning algorithms. Like most of the popular deep learning algorithms people are using over the years, we gathered them all together. And we didn't use them just for classification. Rather, what we did, we use them as a feature encoder. They extract the feature for us. Then we reduce the dimensionality of the features so that we can classify easily without overfitting using this PCA. Principal component analysis is very popular for reducing the dimensionality. So we reduce the dimensionality, and then classifier is basically fully connected layer or MLP, then we classify. So look at the some of the data arrangement. So you can see this is the data arrangement is not a balanced class. We need to first split into train and test set, and then we augment the data to make it balanced, and then we separate the validation and test set. So these are some augmentation techniques. And if you look at the result, in this one, since we are not retraining the model, we are just extracting the feature using the pre-trained models. CheXNet, which is already trained on X-ray image, that performs better than all the other networks. So you can see it is on the top of the list, CheXNet, among the 21 different networks. So if you are retraining, then any of these network can perform better. But if you are not retraining, if your data set is scarce, you just want to use it for feature extraction, then you should use some network which already have seen such data. That's what we can conclude. And then you can see interclass performance. As we expected, like viral and bacterial pneumonia has some classification because there are some overlaying things here. So now this shows us that we just from X-ray images, sometimes it might be difficult to distinguish viral and bacterial pneumonia, but COVID can be distinguished with greater like a sensitivity. There's no issue with COVID, but for viral and bacterial pneumonia, we also seen this earlier. So if you look at the confusion matrix, you can see these two colors, which are a good number actually, viral and bacterial pneumonia, they are cross misclassified because they have similar signature in the lung. So that's why doctors do culture test to get information about the bacteria. Okay, and this is showing the inference time. Although this CheXNet is the best performing network, but it has inference time, higher inference time, but it still is in the millisecond. Inference time in testing time of one single image. Even if you are in the hospital, doctor takes the X-ray, they give report several hours later, but AI can give you in millisecond. So this all the models give results in milliseconds. So I mean, these are real-time applicable devices. So if you look at the signature of the lung from where the model is learning to understand about the bacterial, viral, and normal images, you can see COVID is taking from decision from all over the lung area. Viral pneumonia, where is the infection they are finding, it is taking decision from. So this interpretable model help us to make decision whether our AI model is learning correctly or not. So then we thought, okay, why don't we try a lot of different image enhancement technique and take a conclusion that which image enhancement technique can give us the best performance for this problem. So we tried all the possible image enhancement technique on a very large data set, but in this problem, we didn't use viral or bacterial. We combined all other infections, possible infection. It can be TB, cancer, any form of lung infections, and normal, any infection, and COVID. So this was like a good data set, like a large data set we used, and we tried segmented version of the lung and tried 6 different image enhancement technique with original, and then and the original version also, 3-class classification. So you can see same like previous image enhancement techniques I mentioned, just two technique. Gamma is used in the camera because to give a better real life picture view, gamma used. So that's why we also use gamma. We said, okay, maybe X-ray can be enhanced well by gamma. And BSET is the balanced contrast enhancement technique, is a highly computationally expensive technique. We tried because we wanted to try all possible techniques, but we found that it's actually making the process like a training process very slow because it's a computationally expensive technique. So let's see the result. So in the original image, our result was that, but gamma corrected results significantly improved, we found. So gamma significantly enhanced the, and this is the first paper actually in X-ray domain where gamma is used for enhancement, and it is published in Computer Medicine Biology 2021. And then we tried full model lung and segmented lung. So you can see segmented lung as before. You can see this is 9396, it is 9395, slightly reduced, but still we have better reliability as I mentioned earlier. So here you can see the, if you are training from the full image, if you are training from the segmented lung is always better. So that's actually motivated us. And also you can see one very like evident picture here, image here. This image was originally COVID image, but when you try original image and other enhancement technique, always model fails. Whereas like it always say normal. In one case even lung opacity. But when you use gamma correction, it was identified correctly as COVID. So gamma correction works pretty better. So I'm almost end of my presentation. So this all thing actually tells us that we need a very robust model for lung segmentation, and there is nothing online. The only publicly available data set was 704 images from China, where doctor annotated. But when we investigate that data set with our doctors, several doctors from Qatar Ahmad Hospital, we found that some annotation was wrong. So then we started a big work. We made a data set of 33K, where at that time we reached almost close to 20K, 12K COVID image. Then we have non-COVID lung infection and normal images. We gathered a very large data set, 33K plus images. Then we develop a algorithm which can segment all these lung. And these are the we made it publicly available. You can anytime Google like http://qatarcov.live. This is anywhere in the world. You can use any hospital. Just upload the image. It will immediately segment the lung area and show the infection in the lung. If there is a COVID infection. So you can see it's showing percentage of infection, right lung, left lung, how much infections for different severity of patients. And both the data set we released are also shared here. So you can see the severity of the lungs. The app is publicly available, but it is patented, but we made it publicly available, the output. So anybody can use. Okay, this is qatarcov.live. So that's my collaborators who are Professor Mose from Finland and Sarkan from my Qatar University, and there are other colleagues from Qatar, and these are my researchers. Thank you very much.